Write down every fraction with a denominator up to 1 million, about 500 billion of them. Ask which one lands closest to pi for its size. The champion, by a landslide, has just 3 digits below the line, 355 over 113. 7 correct digits of pi. From a number you could write on a coin. The next fraction that does any better needs a denominator past 16,000. This is not a coincidence. It is a mechanism, and the mechanism is a staircase. By the end, it will also explain your calendar, your piano, and a sunflower. One machine, all of it. Here is the staircase. Take pi. Write down its whole part, 3. Keep the leftover. Flip the leftover 1 over it and repeat. Whole part 7. Flip. Whole part 15. Flip. 1. Then something explosive, 292. Every number unrolls into such a staircase. 3, 7, 15, 1, 292, and on. It is the number's true skeleton, with no decimal system in sight. And the big steps are about to matter enormously. The staircase is older than decimals. It is Euclid's algorithm, wearing geometry. Take a rectangle, 355 by 113. Cut off the biggest squares you can, 3 of them. A strip remains. Cut squares again, 7. A smaller strip, 16 squares, and it ends exactly. 3, 7, 16. That is the continued fraction of 355 over 113, drawn with scissors. When the cutting terminates, your number was a fraction. When it runs forever, as it does for pi, you are holding an irrational, and the staircase is its fingerprint. Chop the staircase early, and you get a fraction. Chop after 1 step, 22/7 school pi. 2 steps, 333 over 106. 3 steps, 355 over 113. Each chop is provably the best approximation of its size in the universe. No search required. And why is that last one so absurdly good? Because the next stair is the giant, 292. Cutting just before a huge step leaves almost nothing behind. 355 over 113 is good, because 292 is big. That is the general law of the staircase. The quality of each approximation is written in the very next step you refuse to take. Feed the machine the square root of 2, the diagonal of a unit square. Out comes the calmest staircase imaginable. 1, then 2, 2, 2 forever. Chop it and you get the ancient diagonal fractions, 3 halves, 7 fifths, 17 twelfths, 41 29ths. Babylonian scribes carved these very ratios in clay 4,000 years ago. And a secret rhythm. The chops land alternately above and below the true diagonal, pinching it tighter from both sides each time. Periodic staircases, it turns out, are exactly the square roots. All of them. Now run the staircase on the sky. A year is 365 days, plus 0.24219. Unroll the leftover, 4, 7, 1, 3. Chop after 1 step, A leap day every 4 years, Julius Caesar. But the staircase says 4 is not the whole story. And indeed, the Julian calendar drifted 11 minutes per year, 10 full days by 1582. Deeper chops give 8 leap days per 33 years. The Gregorian fix, 97 per 400, matches the staircase to within a whisker. Your calendar is a continued fraction with a pope's signature. Every calendar reform in history was, at bottom, someone choosing where to chop this one staircase. The sky posed a harder gear problem long before clocks. A year holds 12.368 lunar months, annoyingly irrational. Run the staircase and chop 12, then 99/8, then the masterpiece 235/19. 19 years, 235 full moons, the metonic cycle, accurate to 2 hours. The Greeks cut it into the bronze gears of the Antikythera mechanism. Hebrew and Chinese calendars still run on it today. 22 centuries of moonlight, scheduled by one convergent. Run it on music. The sweetest interval after the octave is the perfect fifth, a frequency ratio of 3 halves. To build a keyboard, you need octaves and fifths to line up. You need log base 2 of 3 halves to be a fraction. It isn't. So staircase. Chop 1/2. Chop 3/5. Chop 7/12. 7 semitones out of 12. The piano. 12 notes per octave is not a human convention. It is a convergent. The next chop suggests 53 notes per octave, mathematically sweeter, humanly unplayable. Musicians settled where the staircase was kind. Which number does the staircase serve worst? The one with the smallest possible steps, all ones forever. That number is the golden ratio. Its chops are ratios of Fibonacci numbers, and they close in more slowly than for any number alive. The golden ratio is officially the hardest number to approximate by fractions. And that is why sunflowers use it. Seeds packed by the least fraction-like angle never line up into wasteful rows. Worst for mathematicians. Best for plants. Evolution, running its own long experiment, found the number our staircase ranks dead last because hardest to approximate means never falls into a rut. One more portrait, stranger than the rest. Feed in E, the base of natural growth. Pi gave us chaos. 3, 7, 15, 1, 2, 92, no pattern ever proved. But E unrolls into pure order. 2, then 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, forever. The even numbers, marching upward in a guard of ones. Euler proved the pattern holds to infinity. 2 of the most famous constants, one staircase apart. Pi wild, E disciplined, and nobody fully knows why. How good can fractions possibly get? There is a law. For every irrational number, infinitely many fractions land within 1/√5 times the denominator squared. And for the golden ratio, that √5 is exact. No constant better than √5 works for it. Harwitz proved it in 1891. So approximation has a speed limit. The staircase drives exactly at it. And the golden ratio is the police car making sure no one does better. One machine, divide, flip, repeat. Out of it, school pie and astronomer's pie, the leap year, the 12-note scale, and the sunflower spiral. Each one a staircase, chopped at the right step. Decimals tell you what a number looks like. Continued fractions tell you what it is. Every number is a staircase in disguise.